Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Good afternoon, everyone. Welcome to Tah Poe Seminar Series 54 and talk number 4. And today our speaker is Dr. Sikarin Yoo-Kong. And today he will tell us about quantum variational principle, Lagrangian one form. Please welcome our speaker.
All right. Okay. Thank you very much. Actually, I decided to change the topic a little bit because I don't have time to prepare for the announced one. And then I use this one. Actually, I give this talk at the Japan conference. So it's about, the way that we construct quantum integrability, right? To technique that we call part integration. All right, this is a joint work with my student, Thanadoon Kongkum. He is the one who did all the computation, and he's still hanging around there, over there, actually. Okay. All right, so, you may wonder what is integrability, and then what is a quantum integrability, but, let me tell you bit by bit then, okay? So first I'm going to give you like a very brief idea what is the least action principle, standard one, and then the way that we construct a standard propagator, and I'm going to give you the definition of integrability and as a multidimensional consistency, right? And then I talk about Lagrangian one-form structure and its relation that we call Cauchy relation, which is actually, this one is the relation that we can use as a criteria to tell whether our system is integrable or not, right? And then after that, with this Lagrangian one-form structure, we go into quantize it, then we construct what we call multi-time propagator, okay? And with this new type of propagator, we're going to look at the kind of criteria to tell us whether our system is kind of quantum integrable or not, something like that. And then I give you a summary at the end. All right, okay. First, let's let's look at this. Very simple thing. Then, if we have like configuration space, right, in the classical mechanics, you know that actually with the given two endpoint, there is only one true path that actually your system will take according to least action principle, right? The path that actually your system choose is the one that actually the action is extremum. And then if you impose the condition, you will get the Euler-Lagrange equation, right? That very simple thing. And then the part that we call the classical part, that is the classical view, right? Okay. And then if we move to quantum mechanics, so we find out that actually in the quantum level, the behavior of the particle is not is kind of weird because it takes all possible paths from one point to another point. Then we can construct a propagator here, right? Which is actually coming from the unitary evolution here, right? And then, well, with the quadratic Hamiltonian, we can finally find that actually the propagator can be expressed in this form, which is actually, this is kind of the measure, a path measure, right? And the exponential of the S is kind of the weight, probability weight of each part, right? Okay, that is the thing. So I put this here because this is quite important bit, because only for the quadratic Hamiltonian we can somehow derive this equation, and then we finally get this equation. If it's beyond the quadratic one, it's still questionable whether we can expect our propagator in this form or not. That is the thing. All right, okay. And so let me tell you a bit about integrability. Okay, so basically in the classical level, we have a notion that we call Liouville-Arnold theorem, right? And so the integrability of the system defined in terms of the existence of a set of invariants, okay? And with this set of invariants, you can find a set of that we call action angle variables, right? You know that actually in Hamiltonian mechanics, if you can do the canonical transformation to find a set of action angle variable, you can guarantee that actually your system can be solved, right? That is the thing. So the theorem states that though, suppose you have a set of invariant here, put to be F, a set of F here, actually defined on this cotangent bundle, right? And they are all independent, and they are in that we call in evolution. The Poisson bracket between each of them is 0, right? And then there exists a canonical transform of action angle variable here, and it turns out that the action one is a function of Hamiltonian, and then you can solve for the system explicitly, something like that. That is the thing. Okay. So there is a main feature here that we call Hamiltonian commuting flows here, which is actually a direct consequence. Which is actually a direct consequence of involution of the invariants here. So suppose that actually, I said that actually if we treat this set of invariants as a set of Hamiltonian here, right? Because all of this function actually defined on the cotangent bundle, then we can treat them equally as a set of Hamiltonian. Right? Okay. Is it okay now? Yeah, okay now? Okay. Okay, so let me continue. So if we treat this set of invariants as a set of Hamiltonian right here, so what you're going to have this kind of relation right here. And so if you have, well, in the standard context, you know that actually Hamiltonian can be treated as a time generator, right? Because if you have any quantity that I put as a circle here defined on this cotangent bundle, and you compute the Poisson bracket between Hamiltonian, you get the time derivative with it right here. And so now, since we have a multi-time structure, because why we have the multi-time structure? Because we have this a set of Hamiltonian here. Each of Hamiltonian have its own time, right? As well as has its own associated time variable, something like that. So that is the reason why we have the multi-time structure. And so suppose we have a function f here, which is actually define again this on cotangent bundle and as a function of multi-time. So we can find that actually if you look at the time derivative of f with respect to tk, it means that you need to compute the Poisson bracket, the f with respect to the Hamiltonian k, right? If you look at the TL, you do with the HL, something like that. And you do the second derivative. The first one, you do the second derivative with TL, you get this kind of equation. And the second one you do with respect to the tk later, right? And then you find the difference between these two quantities, and you get this one. And you apply the Jacobi identity relation, and then this whole thing can be simply reduced to this quantity. And you know that actually this bracket is 0 because they are in evolution. Then you get 0 here. This means that so the order of the evolution doesn't matter here on this, on this cotangent bundle. It doesn't matter that actually you consider the evolution of the f in the k direction or in the l direction first. At the end, you're going to get into the same point as I put in this picture here, right? It means that this equation actually can be expressed in terms of the Hamiltonian vector field in this way. So it means that this relation gives us another way to look at this Hamiltonian commuting flow, which is actually the bracket of the bracket of this Hamiltonian vector field is actually 0. It means that your evolution is complete this parallelogram here. That is somehow the criteria or the integrability in this sense, and it implies what that is the reason why it's called multi-dimensional consistency, because we have multi-time structure, and it doesn't matter which time that you want to consider first. At the end, you're going to end up at the same point. Okay. And so now we have So this is a whole setup for the Hamiltonian. Next, let's move to the Lagrangian one. Okay. So in principle, right, if we have a set of Hamiltonian, it means that so we can find a set of Lagrangian as well. Then we have a set of Lagrangian here. With this set of Lagrangian, I can write out the action in this way. Okay. And this L is called Lagrangian one form here because we have a multi-time, right? Then I have to sum over possible time variable here, and the gamma is a curve that actually define on space of the time variable or independent variable. Okay, and well, more or less the same way we can construct what we call the Lagrangian vector field, and we can prove that actually they also complete the parallelogram in this way as well, right? Okay, but I don't want to go in detail on this because it's not the main point here in this context, but in principle we can do that. And so now, if we impose this condition, right? And apply Stokes theorem on this action, we're going to get this relation here, and then it turned out that actually you will get this one, which is actually this is the two-form quantity, and is it going to be zero if this quantity must be zero? And then this is nothing but we call the Cauchy Lagrangian one-form Cauchy relation, right? Which is actually I would say this can be considered like a Lagrangian version of the Hamiltonian commuting flow, right? Okay, so if you look at the curve, actually, the curve on the space of independent variable, Ti and Tj here, you have two curves. With this relation, it means that the action of this part and the action of this part are the same. The value of the action are the same, right? So it doesn't matter that actually which part that you choose to go from here to here on this space, it's going to give you exactly the same value of the action. That is the thing, okay? Well, you have to keep in mind this space of time variable, not the tangent bundle, right? Okay. But on the tangent bundle, you have only one single true part, the classical one, right? But this on this space you have well, any part that you can take actually. Okay, so let me give you the example of the integrable system, which is actually the well-known one is the Colangelo-Moser system, and which is the system of n particle in 1D actually, okay, and with like repulsive interaction somehow. And for this system, I give you the first three Hamiltonian in the hierarchy here. The first one is the total momentum, and the second one is the Hamiltonian itself, right? Because this, why I call it Hamiltonian itself, because this is the standard definition of the kinetic energy, right? And then this can be considered as an interaction or the potential term. And if you go beyond H2, you go to the H3, you can see that PQ is no longer the definition of the standard kinetic energy anymore. And there is a mixed term between P and Q here. And then if you go further, you're going to get much more complicated form of Hamiltonian, but I give only the first three here. With this first three Hamiltonian, there is a way to find this Hamiltonian, but I skip it, but I give you right away. And then with these three Hamiltonian, you can find a set of Lagrangian as well by doing like a Lejeune transformation, okay? But the thing is that for this system, the Lagrangian will start with the L2, which is a standard Lagrangian, and there is no L1, because if you look at the Hamiltonian, this one, right, you cannot perform the Lejeune transformation properly because you cannot find the inverse of it. Then there is no Lagrangian associated with this Hamiltonian there. Okay. Then we have for the L2 and L3 for this Colangelo-Moser system, and there is a mixed derivative here. If you look at this, there is a mixed derivative. I put the dot as a derivative with respect to T2, and the bar is a derivative with respect to T3, something like that here. Okay. Now with Okay. So in long time ago, 10 years ago, I would say, my advisor, actually Frank Niehoff, proposed a new form of propagator for the discrete integrables in the conference that at Newton Institute at Cambridge, that actually for this kind of structure of Lagrangian here, which is actually associated with the multi-term structure as well, we could have a new type of propagator here, which is actually you need not only take over possible part of the X, but you need to take over possible part of the time variable as well. That is a proposal right here. It means that, so if you look at this is suppose this is a configuration space where there is all possible path that you can take here, and then you have to take all possible path on the space of time variable as well, right? That is a thing. Then the interesting is that if you're doing this way, it means that you treat the time variable and the space variable on the same equal footing, right? Like we do have in the relativity now. And so the idea actually, he took it actually from this Lovelace paper on, well, well, actually the idea of the Lovelace, he tried to find a new way to formulate this kind of stuff to understand, to study quantum gravity somehow, something like that. But well, anyway, what Lovelace did is, well, he take a background independent. It means that, so, well, if you have QT here, right, you can change to a new set by introduce a new variable that we call tau, which is actually called a parameterized variable. By doing this, it means that now you have a new set of variable Q and T, right, which is on the same equal footing now, which actually both depends on the new variable tau. By doing this, you can transform the action, and then you get new action in this way, actually. Yes, I think I might be a typo here. I don't know. I believe it should not be here. This term should not be here, I think. Anyway, so let's have a look for very simple system here, like here. If you do this kind of trick that Lovelace did, you're going to get this kind of new type of Lagrangian here, and you compute the propagator. Your propagator will turn out to be that you have to sum over possible of the Q and the T, right? That is the thing that what he did found. And then you can reduce actually this one back to the standard one, right? You can reduce back, right? Because the way that you can reduce means that you can integrate out the T variable in this, and that the part of T variable is going to be nothing but the prefactor in the propagator in the standard one. Okay, that is the idea, I believe. Okay, and then he and King study a system that called KdV equation, and they impose some periodic boundary condition. From this KdV equation, they find out that the result of that periodic condition, they got 2 times harmonic oscillator here out of it, and then they can show that actually the propagator for this system possesses what we call path independent feature. It means that, so if you have a discrete curve like this, and if you have a loop, you can take out the loop because this gives us identity here. It means that the total path is going to be the solid line, something like that. Because you have this condition out here, okay? Then it means that the loop is going to give you identity, that kind of thing, all right? So, but this is on the discrete setup. So what we set out with Tanadon is that we need to extend the idea to the continuous version of this. And we have these 2 Lagrangian as our proposal to work with. All right, so now we just define the continuous version of multi-time propagator. So suppose let this out to be Lagrangian 1 form right here, and we also introduced a variable h, which is actually the parameterized variable in this way. We say that actually a propagator for this Lagrangian one form will take the form, it will take this form, which should look a bit complicated a little bit, but the thing is that we have only one fancy D here. We don't have two fancy D like Nihal proposal, and the reason why I'm going to tell you later. But effectively, what it means by having this kind of new fancy D is that we have also take both part of the Q and the T as well. That is a thing. All right. Okay. And so that the thing, but I would like to emphasize again. So we can put things in this way if we work with the quadratic Hamiltonian, right? And you see that actually in the Calogero-Moser system, there is a Hamiltonian actually beyond the quadratic one. Then I put a conjecture that actually for the one that beyond the quadratic form, we also still put the propagator in this way. But the difference is that this kind of a wave could be different from the quadratic one. That's my conjecture, but we need to give a solid proof on that, because there is a way that we can perform integration beyond the Gaussian one. There is a way that it means that there might be a way that we can put things into this way. Anyway, okay. So sorry. And then with this definition of this new fancy D here, which it look really terrible here. And so it's really complicated and very ugly, I would say. But I'm going to explain you for a very simple case, like a 2D case, that you're going to get a flavor how to construct this D, because this D is going to take in arbitrary n dimension, right? So suppose that we have this 2D grid here, okay, which is divided by n and n here, and then this T1 and T2 direction, and the width which we take to be epsilon 1 and epsilon 2 in this way. So we say that actually, if you look at this kind of the first part, they actually go around the corner here. It means that you have to take the propagator, start from this 0, 0 point to this corner point, right, in one direction, in T1 direction, and then you go up to the end point in T2 direction. It means that your propagator can be expressed in this way, right? This is for the T1, right, along this, and this factor is for the T2 along this line, and then integration of this bit is the integration of this corner point, right? And then this is the exponential part, actually nothing but actually you can express into the Lagrangian one form, okay? And then you get now for this part, you can say that actually I call K1 here. You can put a thing in this way, okay? Next, okay. So that, and now I also define a family of parts here that I call fancy B1 here. And I call that this only part is a member of this family B1. And in this family of B1, there is only one configuration of part that's possible, right? Because it just go like this. So, okay, next, let's have a look at this part here. And this way, which is called gamma again, but this one belongs to a new family of part they call B2 here, right? And if you write out the propagator K2 for this part, you find out that actually the first term is nothing but the K1, and you have the extra the second term right, out of this, because you have a path that go up here and then up here, right? That is the thing. Okay, and so then you somehow, somehow here you can, I would say you can compactify this relation to be a single line, okay, by, and then we have this one, okay. And with this one, it means that you include also a family of B1 into this already, into this propagator into it already. It means that if you move this vertical line to this side, it means that your K2 will be your K1, right? That kind of thing. And we go further for a more complicated part here. And then we have K3 here. And again, we have 3 terms, I believe, the first term, second term, and the third term. And I say that actually this kind of new configuration of part belong to a new family called B3 here, okay? And I'm doing this kind of same trick. I can somehow reduce this K3 into a very simple term, but the gamma will belong to a new set of family of part by the union of a set of B1, B2, and B3 here, okay, with this one, okay. And by keep doing this kind of process, okay, so you will get K5, which is actually, well, it's going to be lengthy, and it's very, look not really friendly anyway, but anyway, you're going to support a pattern, okay, of this propagator, and you can reduce again for the K5, and then you get exactly the same, that actually the part going to belong to this union set of family. So I would say at the end, by doing this kind of thing, so we get all possible configuration of the part that actually start from this point, go out this way, and then all possible way up to this point. And then we can explain into this form, okay? And so we put here this factor here to be to make sure that actually our propagator satisfy the normalization condition, okay? All right, so this is the idea. But the thing is that what I did here, what happened? What I did here is just a half of it, because I start from this T1 direction, right? But I can do the same trick with if I start with the T2, right? It means that I need to taking into account all the possible path, or actually start from the T2 direction, right? But I just do nothing, because it's going to be the same. It just interchange the variable from T1 to T2, right? And then by apply the symmetry condition. So at the end, our fancy D going to be this one, right? Which is the first bit is coming from, actually you start to flow at the T1 direction, and then the second bit you start to flow in the T2 direction. You sum them up together, you will get this our fancy D here. This is for the 2D case. And then with this idea, you can extend to any to the 3D space and beyond that, and it's going to be complicated as I gave you earlier, that kind of thing. Okay, next, so now we have this a propagator here, right, which is have a form more or less the same with the standard one, I would say, but we have to keep in mind that actually this new fancy D here that actually include all possible part of the Q and the T in here, right? And this is the action or the Lagrangian one form here. So with this form, we cannot do well, it's not really useful with this form. That what going to do next is we're going to apply semi-classical approximation, right? Because with that kind of approximation, you can get the explicit form of the propagator right here. So what I did is that, so I turned this propagator into in terms of the parameterized variable s, right? It means that, so now the propagator become a single term in terms of the s variable now. It means that this still is mean, so you have now here more or less the same with the standard one. And then we can apply the semi-classical approximation, right? I mean, the fluctuation around the classical part, and the Q, this Q factor is nothing but actually the quantum fluctuation around the classical part here, right? Here. And then, well, you see that actually, in principle, you can do this integration because this is the quadratic one, right, in principle. And so, yeah, it means that, so you can do the integration and then you will get this calculation, which is actually the standard of what we have in the one-time variable, in one-time case here. Okay. So now we put a theorem to be a criteria for the integrable system, where to consider whether our system, our quantum system is integrable or not. So suppose we have again a set of Lagrangian one form, and we actually and this gamma is any part that actually belong to this fancy B, which is actually a family of parts to connect between these 2 points on the time space, right? So we find out that actually for the loop part, right, on the space of time variable, you will get identity, right? Yeah. And the S is a surface actually bounded by that loop part, okay? So next we're going to give you a proof. A proof is very simple. If you consider, first you consider part gamma, you get K gamma here, and then we take also the semi-classical approximation, right? We get a Q gamma here, right, this way, and then we take another part, you call gamma prime, which is these 2 parts sharing the same endpoint, right, on the count space, and you get this K gamma prime with this Q factor Q gamma prime here, right? And then with the closure relation, right, of the Lagrangian one form, it means that the difference between this action must be 0, right? Because if the closure holds, it means that you can turn this integration into the closed loop here, and then you get this to be the closure relation. That is the thing. And then once you get that this S gamma and S gamma prime is the same, then it means that Q gamma and Q gamma prime is also, they are also the same, right? Because it depends on this derivative. Then finally we get that actually K gamma and K gamma prime are the same. Then kind of finish the proof somehow. No, not really. Actually, that we call we have 2 different parts, and then we get the same propagator, right? And then for the loop, actually, for the loop, then you're going to consider this kind of for a propagator right here, and it's really tricky to turn this bit into this relation here. We need to turn this difference of the f of the s into the differentiable. I mean, okay, here in this way, and then if you put this relation back into this equation, it turns out that actually you will get the delta function, and then you get identity out. Is kind of finish the proof here. All right, so now we say that if our quantum system is integrable, the multi-time propagator have to obey this structure, or the loop part is going to give us the identity That is the thing. Okay, now that is what so far is very abstracting. Now we look at a concrete example here. With I mentioned earlier, with this two-time harmonic oscillator, which I mentioned earlier here, L1 and L2 here. And now the Q is a function of Q1 and Q2 in this way, okay? And omega is a constant, omega 1 and 2. So the quantity that we would like to consider is this bit, which is actually, this factor actually in the is the exponential factor of the Q, right, of the quantum fluctuation. And it turned out that actually we can write this one in this way, right here. Right, then it means that the Q gamma, right, for this two-time variable can be expressed in this form, okay? And the Y is nothing but the fluctuation from the quantum, the fluctuation from the classical part. And so, if we do further a more further step, then we're going to get this relation by doing integrating by part, right? We're going to get this. I think this should be T2. This is a typo. It should be T2 anyway. Anyway, so now the point is that, so what we need is we need to find the functional Y that actually satisfy the boundary condition that we consider. And it turned out that if you look at this 2D grid here, 2D space, and you look at this part here that I call gamma A, we find out that actually the function Y that actually satisfy the boundary condition here can be expressed in this form, okay? And it's not difficult to show that actually there is orthogonality of the Y as well. And once you put this Y into the Q equation, you can compute the Q gamma A to be in this form. Okay, right. And next, if you look at the part that actually go up in this way and then go to this way, then I call this gamma B. We still can use the same Y, which it actually still satisfy the same boundary condition. Sorry. We still can use the same Y, which still satisfy the same boundary condition here. And it turned out once you put this Y into the Q factor, it turned out that Q gamma B is exactly the same with the Q gamma A, right? Okay. And so next we consider this much more sophisticated part here. And it turned out that for this particular part I call gamma C here, you need to take your Y into this form. Right? You have to split into interval here, right? But eventually, when you put this Y into the Q factor equation, and then it turned out that actually this Q factor for the gamma C is exactly the same form with the 2 previous one. What does it mean? It means that, so for these 3 different parts, you get this factor are the same, right? And you know that by have quotient relation, the action of the part A, part B, and part C are the same as well. It means that your propagator are part independent, right? On the space of time variable here, right? That is an example that we have given here, right? But well, you have to keep in mind that this is only for the quadratic case, and beyond that we don't know yet how to deal with beyond the quadratic one. Okay. So let me put the summary. So well. We know that actually the Lagrangian is not unique, right? That is the thing. And you can have different Lagrangian, which it actually give us exactly the same equation of motion, right? So But in the context of integrable system, you also have this kind of non-uniqueness property of the Lagrangian. But in this context, you have a set of Lagrangian, right? And you're going to have a variety of different sets of Lagrangian that we call space of Lagrangian, right? Which should actually give you exactly the same set of equation of motion. But there will be only one set of Lagrangian that satisfy the Cauchy relation. That is the one that we need, right? Otherwise, then we cannot actually show this kind of feature, because this kind of feature rely on the Cauchy relation here, right? Then we need a unique set of Lagrangian that satisfy the Cauchy relation from all possible set of Lagrangian that give you exactly the same set of equation of motion, right? That is the first point. And this is the reason why this kind of structure gives us called on top of the classical variational principle, in the sense that this special set of Lagrangian plays a role of critical point resulting part independent of propagators on the space of independent variable, and it has been called like quantum variation by King and Niehoff. All right, this kind of new feature that we have here in this context. Okay, and so, well, the thing is that so the propagator that we have only one single fancy D, right? We should actually include all possible parts from space and time, right? It's not the same one with Niehoff proposed in 2013 there. That is the same thing. But anyway, they do share more or less the same feature, because in the discrete case, they also show that the loop, discrete loop can be taken out. There is no contribution for the loop for part on the space of time variable. And for the continuous case, we can also show that actually for the loop can be taken out as well. This is sharing the same feature there. And that's all. Oh, sorry. That this is a different. And this is my cat. And thank you. Okay. If you have question, please.
Okay, thank you very much for a nice talk. If there are any questions from the audience, please feel free to ask.
Is my really? Yes, please.
Okay.
I love simple question.
Yes, because I don't know much about your topic.
Yeah.
Up to my understanding, you analyze the integrability of the system because one of the reason because you want to find the form of the Hamiltonian or Lagrangian. The general form of Hamiltonian or Lagrangian that can be integrated, right? This is correct.
Not really quite. I would say that actually with the given set of Hamiltonian and Lagrangian, we need to find a condition to test. That's what I did here.
Okay. And which motivation of your Hamiltonian or Lagrangian in your analysis? The motivation for the form of Hamiltonian.
The motivation is actually integrable system is it depends on field that you consider. If you consider like point particle system, you're going to have what I did show here, like a Calogero-Moser system. And if you're working on the nonlinear science, right, you're going to have like a KdV equation or Kp equation. And if you have, if you study quantum field theory, you will have a system like a Chen-Simon system that actually also integrable. And we can show that actually there is a recent work from Niehoff that actually they can show that actually Chen-Simon can be put into the multiform structure, and they can show that actually they obey the Cauchy relation as well. That kind of thing. But it depends on the system that we consider. But what I did here is for the point particle. Okay, it's a very simple step, not the like a first baby step here.
Yes.
Okay.
You can use your analysis in also classical field theory, right?
That what we did try actually with the Tanadon. That for the classical field actually is going to be like a two-form case. For the one-form case, it's going to be like a point particle system, and the two-form case is going to be like KdV equation that we call. You can consider that field as a field equation, and we did try to analyze with that kind of system, and it turned out to be very difficult to construct this kind of new type of propagator for the classical field. It's very tricky. I mean, but we actually did have some progress on that, but not really what I expect. Actually, we need to investigate more.
And okay, the last, did you also consider the case where there is a higher order time derivative of the numerical variable in Lagrangian?
I did not actually. Yeah, I have seen this kind of Lagrangian, like you have like a Q double dot square, something like that, right?
Yes.
Yeah, that is not not in this my scope of work actually. But I think there is a group of people actually working on that. I don't know what is called that beyond. I don't know, but I believe something to do with cosmology, right?
Yes. You can modify gravity. Have something like.
Okay.
Okay.
Right.
Thank you.
Yeah, thank you.
Is there any questions?
Smile.
Smile is a signal.
Okay.
Okay. Probably I'm not sure. So for your work, the condition that apply the integrability is that the Cauchy relation that
Yes.
and when it's applied to investigate the multi-time propagator in the multi-time space, it turns out that correct me if I'm wrong. The space of the time variable is flat.
Yes, it's Rn, right? Yes.
Yes, it is a Euclidean metric signature.
Yeah.
So, like if I mean analogy to the GR, to the GR, it is a flat matrix. I mean, in GR there are many quantities related to the metrics of the space-time, like the Riemann curvature and like the torsion tensor as well. Can I mean, if the space is, I mean, totally flat and the torsion free related to the GR, I mean for the integrability to be valid, the space need to be flat. Not have the curvature at all, right? So does that mean that in GR is not integrability, is not integrable in the GR? I mean, can I refer to that?
I don't know actually. Because what the space that we're talking about is space of independent variable, right? It's a
It
time
doesn't get a
variable.
time.
Yeah, and then we still have another space, the upper one that we call configuration space, right? That actually you can project the part on that space into that. Let me draw you a picture here. So we have so we have suppose this is suppose we have two times, okay? So you have a curve here, all right, and then you can project it into this plane. You have a curve here, which actually T1, T2, and T1 double palm, T2 double palm, and then you have this Q palm, and then this Q double palm. Yeah. You have this kind of thing. And this is totally flat, as I mentioned, and then you can take any part of this, well, and the action remain the same. But on this particular space, for the classical version, you have only one single part. You still have one single part for this. But once you project this part on this space, you can go any of it into. And so I'm not sure about your question about the GR, because GR is we have, I think we have this different kind of space, right? Because you have a manifold, because the manifold here, actually, the manifold here that we consider is the configuration space, which is n dimension, right? And then if you take a part, then if you take a propagator, you have to sum over possible part on this configuration space, right? Which is a space that defines the Q variable here that I mentioned, Q here. But there is no, well, the time variable somehow is already embedded in this Q somehow. It's not the space-time like in the context of relativity, I believe, in GR. Then I'm not sure that we can say that kind of integrability condition. Well, but there is a group of people they would like to prove that actually the Einstein equation is integrable, but it's too complicated. I mean, the equation is so highly nonlinear, then they don't know how to deal with that kind of nonlinear effect, and yeah, that kind of thing. I don't know whether I answered your question or not, but okay.
Thank you. Is there any further questions? So if not, I would like to say thank you for our speaker again, and okay, let's say thank you to our speaker. And enjoy your snack. And today we have the supporter from our supporter, but we need to pay our supporter. With friendly price.